We will now start section 5 on the analysis of sampled data systems, and you will see that it's the last big section before we actually start talking about control design. As you have seen in last year's course of Fundamentals of Control Theory, there are two main types of concerns when you talk about control. The first one is, well, tracking a reference signal, and the second one is rejecting a disturbance. The disturbance can be at the input or the output. So we'll start with setpoint tracking. In this slide, we assume that we have a controller C of Z that is acting on the control error, setpoint minus Y of Z here. That is the, well, process output that is to be controlled, and this controller produces an X of Z. So we have started from a continuous description of the process, and we have ended up with a C of Z. This is a controller that you can implement on a processor. As I've said before, there are two ways to obtain C of Z. Either you do a continuous time design, you end up with a C of S. This is what you've done in last year's course of Fundamentals of Control Theory, and then what you do is, well, obtain a discrete time equivalent description of C of S. We have seen that there is another way to go, and it's to obtain a discrete time equivalent description of the process PS, and since we're going to use this as a vehicle to obtain CZ, you should take into account the zero order hold mechanism, right? Even if very often I will simply say P of Z for ease of notation. And then we do direct digital design and we end up with C of Z. The advantage with the second method is that you can allow for a TS that is in general larger than with the first approach. So whatever the mechanism that you've chosen to construct C of Z, if you want to evaluate its performance, right, on the sampled system, okay, so if you want to consider the sampled closed loop system, well, you have to consider a process that is the zero order hold equivalent description of the original system. So a description that will take into account the zero order hold mechanism. Okay, so if you want to evaluate your controller in tracking, well, this is the simplified control scheme that you have to consider, where P of Z is the zero order hold equivalent description of the original system. Well, you have noticed that I'm working with a P of Z and not with an H of Z. Well, this is because here in the SQL we want to stress process. Okay, if I use H of Z, I stress the fact that the impulse response in discrete time is H of K. Here in the SQL we will work with the acronym P of Z to denote the, well, process in discrete time. And when I write P of Z, I will always assume that it is the zero order hold equivalent description that is taken into account. As you can see over here, we have seen that you can rewrite it as follows, and here you can see that this is also equivalent to the, well, step invariant description of the process. They are both equivalent. This is really important because when we assess a controller C of Z, it is important to take the zero order hold mechanism into consideration. It is important for a controller to be able to track a reference signal, but it is also important that it is capable of rejecting a disturbance. There are different types of disturbances at the output, but here we'll consider, well, disturbances at the input of the process, and they are called load disturbances. Well, these load disturbances appear at the input of the system, well, just after the zero order hold mechanism. Okay, this Ws here can be seen as the Laplace transform of some signal Wt, that is the actual load disturbance. Okay, so we would like to rewrite and to simplify the closed loop system using my transfer function P of S, right, that takes into account the zero order hold mechanism. So what you can do is kind of say, well, we can replace this by a disturbance at the output now, that is simply PS WS, right? And then you take it outside of this box here where you have digital to analog conversion and analog to digital conversion, and you can do this by taking this one, taking the inverse Laplace transform, evaluate at t is equal to kts, and then take the z transform. And what you have done here is kind of take this input load disturbance and you have brought it at the output where it is kind of modeled as an output disturbance. Okay, this is kind of annoying because we would like to see them acting over here, and we will see in the next few slides that you can kind of approximate this to have here an, well, equivalent discrete time load disturbance acting on the system. Well, this is the simplified control loop we end up with for the load disturbance configuration. We have kind of transformed this load disturbance in an output disturbance, and we have been forced to do this because the load disturbance acts on the continuous time system, therefore after the zero order hold mechanism. So if we now combine set point tracking and load disturbance, we obtain the following, well, control loop or closed loop, and you can write the input-output relation as follows. This will be called the complementary sensitivity function T of S, and this will be the sensitivity function, and we'll come back to this later. It is very important that you are able to construct, for instance, this kind of input-output relation. So for instance, to obtain the closed loop transfer function that goes from RZ to YZ, what you can do is just consider this closed loop with one input, so you kind of forget this input over here, and then you write the output. So y of z is equal to p of z c of z. Okay, and then what is entering is epsilon z, but epsilon z is rz minus yz, right? So you bring everything on the other side, so you will have 1 coming from this one plus pz cz yz, it goes to the other side, so we have pz c of z times y of z, and you have pz c of z r z. Okay, so you end up, of course, with this relation over here, and you can do the same kind of exercise for the relation between this signal over here and the output y of z. And as I've said, this yields the complementary sensitivity function T of z and the sensitivity transfer function S of Z. The only way to take the load disturbance, okay, it's over here, it's the Laplace transform of this signal here that is acting at the input of the continuous time system, into account, is to transform the closed loop here in discrete time as follows, and we have kind of transformed this influence to a disturbance acting on the output. This is the exact relation. This is a bit annoying because when we work here in discrete time, we would like to see this load disturbance as something that will be acting here at the input of the system. So an approximation that we can make is to replace this by P of Z, W of Z, right? And then we can rewrite it as follows. This is really an approximation because, as you can see here, well, there is no influence of the zero order hold. This is kind of normal because this one is acting behind the zero order hold, whereas this one here is really taking into account the zero order hold. So this is really here an approximation. Using this approximation, this is the, well, simplified closed loop system that we obtain in discrete time, and it is this one that we'll use, well, to look at set point tracking and to look at load disturbance rejection. These are the two transfer functions that I have introduced before. The first one is the sensitivity function, and the second one is called the complementary sensitivity function, and you can see that if you add them you have 1. Those two transfer functions, those two sensitivity functions, will play an important role later on in the course, and we'll see what kind of specifications you can impose on these two transfer functions. I have introduced them now because I'll probably end up mentioning them when I'm presenting the course. Well, in this section we look at steady state accuracy. So steady state means that all the transients have disappeared. So it's when, well, time goes to infinity, and accuracy, of course, here means that we are looking at this signal over here. It's set point minus the signal that we control. So steady state accuracy, we want the, well, signal here, epsilon or E of k, to go to 0 when k tends to infinity. So this is the closed loop system that we are considering. We have the reference input, that's the set point. We have disturbances at the output, and we assume here that D of Z is the Z transform of D of K. And we have load disturbances, WZ, and we assume that WZ here is the Z transform of a signal WK. So what we can do is write this epsilon Z here as a function of the input signals. Well, normally you should be able to do this, but let's, for instance, compute this transfer function here, and I'll leave you the two other transfer functions as an exercise. So epsilon Z is really RZ, right? So looking over here, minus, okay, since we are looking at the influence of RZ, we forget about these ones, right? So we have minus PZ CZ epsilon Z, right? We bring everything on the other side. 1 plus PZ epsilon Z is equal to R of Z. So indeed we have the correct transfer function. Notice that in here the transfer function that links RZ to epsilon Z and DZ to epsilon Z is exactly the same. So we'll be able to consider set point tracking and rejection of output disturbances at the same time, because the same transfer function is involved. For load disturbances, it's another transfer function, so we'll have to deal with load disturbances in a separate way. We will assume that the process B of z is described by this transfer function over here, where a and b are polynomials, and we'll assume here that this system has a number of poles at z is equal to 1, so that it has a number of integrators, right? We will use a controller C of z that has following transfer function. So again, here C and D are polynomials, and well, this controller has also a number of integrators. The difference is, of course, is that the number of integrators in the process, well, is really process dependent. It's not something that you can choose, right? It's fixed by the process. But here we are designing the controller, so the number of controllers poles at z is equal to 1, so the number of integrators in the controller is really something that can be determined by the one that is doing the design. So this quantity here, LC, that we'll call the type number of the controller, needs to be determined, and it will influence steady state accuracy. And so what we'll do now is have a look at how you should choose this LC in order to have steady state accuracy, first in set point tracking and then for load disturbance. The type number of a system is the number of unit circle poles of its transfer function, so the number of integrators in the system. So remember that P of z has been written like this. It's B of z, and the denominator is AZ, and then you have a number of integrators, and there are LP integrators, so the type number is LP. We had something similar for C of z, the controller. Two polynomials that are involved, C and D, and then there are LC integrators in the controller, right? So the type number is LC for the controller. The loop gain is simply the product. So this is important because in a closed loop, what you'll have is the process, you'll have the controller in front, and then you construct your closed loop system as follows. And what we call the loop gain is, well, in French, la chaîne directe. Okay, so this is this transfer function over here, and without a surprise, the type number of the loop gain is simply LP plus LC. Remember that P of z is written as a polynomial BZ divided by a polynomial AZ times a number of integrators at the denominator here, and we have something similar for the controller. So CZ divided by DZ, and then Z minus 1 LC. What we'll call the open loop steady state loop gain really is to take this loop gain, so PZ times CZ, and then multiply by this quantity so that the influence of the integrators disappears, and then we take z that is tending to 1. This is because we want steady state behavior, so I refer you to the final value theorem in discrete time. Okay, and if you look at that, of course this will be BZ divided by AZ times CZ divided by DZ evaluated at Z is equal to 1. right? And we'll call this quantity gamma. Depending on the type number of the open loop system, so depending on LP plus LC, gamma will have a different name. If this type number is 0, this means that there is no integrator in the process and no integrator in the controller. Well, this gamma will take the name position error constant. If there is one integrator in this loop gain, either in the process or in the controller, then gamma will take the name velocity error constant. And if, well, there are two integrators in the open loop system, and they can be divided over process and controller, or be all in the process or all in the controller. Well, if this type number is 2, then we'll call gamma the acceleration error constant. And we'll come back to these denominations, these names over here later on in the course, and you'll understand why it's called position error, velocity error, and acceleration error. So what we'll do now is first consider set point tracking, right? So we want to design a controller that follows a reference input R of k. Its Z transform will be R of Z, okay? And, well, we want the error here, E of k, to tend to 0 when k is tending to infinity. Okay, so here we speak about follow a reference input, but remember that the transfer function that links rz to epsilon z is the same. The sign is different, but the transfer function is the same as the transfer function that links dz to epsilon z. So when we talk about designing a controller that will follow a reference signal RK, we're also talking about a controller that will be capable of rejecting an output disturbance. And this is because the two transfer functions that are involved are exactly the same. So we want to follow a reference signal RK that is a polynomial of degree MR with 0 steady state error. So what does this mean? Well, if the degree is 0, we'll want to be able to follow a step signal. If MR is equal to 1, we want to be able to follow a ramp, and so on. Okay. Equivalently here for DZ, we want to reject a disturbance that is also polynomial in T of the same degree as here. So the Z transform of this reference input set point is called RZ, and it will take the form that is over here, right? So you'll have a number of, well, you have Z minus 1 to a given power with some polynomial that will be of degree D smaller or equal to MR plus 1. So let's have a look at what we mean by this. Well, remember that we are considering set point tracking or output disturbance rejection, right? And let us, for the sake of the argument, say that we are considering set point tracking, and we want to be able to follow a reference signal RK that is, well, polynomial in T of degree MR, and typically we'll consider MR is equal to 0. This corresponds to a step signal, and MR is equal to 1, and this corresponds to a ramp signal. This one is hardly ever used in practice, so we'll leave it aside. Okay, so we had considered R of Z is equal to a polynomial R of Z divided by Z minus 1 M mr plus 1, and this one is of degree d smaller or equal to mr plus 1. So let's check if this makes sense. If we have here a unit step, then you know that it's, or you should know, or you should be able to find back that its z transform is z over z minus 1. So this polynomial over here is simply z, and it is of degree mr is equal to 0 plus 1. So here we have d with equality, right? So this makes sense. And we'll take the other one. Let us take mr is equal to 1. So it's polynomial in t of degree mr. So we have in continuous time t u t. We have to replace t by k t s. So we have a ramp signal over here. And again, you should be able to find out that its z transform is given over here. So again, we have transfer function of this form. Okay, so I have a degree 2 over here, but mr is equal to 1. So check, this is correct. And the polynomial over here is z times ts, and here it is of degree 1, mr plus 1. So the degree is indeed smaller or equal to 2. So this makes sense. So in our case here, we'll consider only reference inputs, set point signals that can be a step and a ramp, although the theory can also handle, well, set point signals that would be behaving as a parabola. Well, it goes without saying that in practice you cannot use an actual ramp signal, as this one is going to infinity. In practice, the signal at the input of the closed loop system, so the set point, will be a truncated ramp, and it will look like this. Okay, so at some stage, well, the set point signal becomes constant again. But we use this type of signal to kind of study steady state accuracy, and of course we expect the accuracy to occur as fast as possible in this ramping stage of the set point signal. Well, we are now in a position to look at steady state accuracy for set point tracking. Remember that you have the similar term here, 1 over 1 plus pzcz d of z. So studying set point tracking is also, well, looking at the same time at really disturbance rejection of output disturbances. So what we do over here is consider this relation over here, and what we can now do is plug in our descriptions of the process, the controller. Remember that LP is fixed by the problem. LC is something that you can well choose, and what you have over here is R of Z, and here MR, well, tells you which type of reference signal you want to be able to follow. MR is equal to 0 is you want to be able to follow a step signal, and MR is equal to 1 is you want to be able to follow a ramp signal. If you put everything under the same denominator and you do the calculations, this is what it looks like. Okay, and we were looking for, well, the steady state error, and we want a 0 steady state error. So we want that this quantity over here, the error, this is the set point minus what is controlled, to go to 0 when k tends to infinity, right? And this can be obtained from this relation by looking at the final value theorem. So what you see over here, if you wonder, you shouldn't wonder, is really the final value theorem, and this will allow us to find the LC that is necessary in order for your steady state error to go to 0 given a process and given a reference signal that you want to follow. So this is the expression that you had found for epsilon z. We want a 0 steady state error, so we need to make sure that this quantity over here is 0. But this will really be the steady state error. So what we have to do is take this expression here and multiply by z minus 1 from here. Okay, so this will cancel out with the plus 1 over here. Okay, and then we have to take the limit when z is tending to 1. So what we'll do is consider two situations. The first one is LP plus LC is equal to 0. If this is the case, well, then what you have is this one over here will disappear, right? And this one will disappear, right? And then you have to let z tend to 1, and this is what you will obtain. You're left with the 1 over z minus 1 to the power mr. Okay, so you replace everywhere with z is equal to 1, and you'll end up with this limit over here, and this is 1 over z minus 1 to the power mr. Note that this quantity over here is linked to gamma, the open loop steady state loop gain, and this quantity here is 1 over 1 plus gamma. Remember that gamma was B1 C1 over A1 D1, right? So here we have considered the situation where LP plus LC is equal to 0, and this is what we obtain. We can now have a look at the situation where LP plus LC is larger than 0. Okay, so in this denominator here, factor, well, if LP plus LC is larger than 0 and you replace z by 1, this one will disappear over here, right? So if you replace everything or z by 1, you'll end up with this quantity over here, and here you have z minus 1 to the power L plus LC, and here at the denominator you have z minus 1 to the power mr plus 1, but since we are computing the steady state error, we have to multiply by z minus 1, right? So this one will disappear with this one. Okay, so when we look at the powers of z minus 1, well, we have LP plus LC minus mr, and we end up with this expression over here. Remember that LC is something that we can choose. Okay, so in general we'll put an integrator in the controller, and you can see over here that if you choose LP plus LC minus mr larger or equal to 1, right, this steady state error will be equal to 0. So if you take LP plus LC is equal to mr, because you will not put more integrators than necessary, and you have it's sufficient to take the equality over here, well, if you take this relation here and you choose LC to be mr plus 1 minus LP, okay, of course this has to be positive, right? So this is why we have this max. Well, you're going to impose a 0 steady state error. Remember here that LP is the number of integrators in the system. Okay, so that's problem dependent. It's not something that you can choose, and mr comes from your specifications. If you're interested in following a ramp, for instance, mr will be equal to 1. If you're satisfied by just following a step signal, then MR is equal to 0. But anyway, by choosing LC in this fashion, you're going to impose a 0 steady state error. Well, these are the two situations that we had considered. LP plus LC is equal to 0, so there is no integrator in the loop. And then LP plus LC larger than 0, there is an integrator in the loop. And this integrator can either be in the process, in the controller, or if there are several integrators in the loop, you can, for instance, have one in the controller and one in the process. In here, you will see that for set point tracking, we're just looking at the amount of integrators in the loop, and we don't care if they are in the process or in the controller. You will see that for load disturbances, well, this will be quite different. Okay, so if you look at the first relation, right? So we look at this line in this table over here. You can see here that you will have a finite steady state error only if you're using a step signal. Okay, the error will be finite and non-zero. If you're trying to follow a ramp signal, for instance, and you have no integrators in the system, well, the steady state error will be infinite. Now we consider the second relation over here. Let us, for instance, have a look at the situation where we have one integrator in the loop. So we have to consider this situation. Okay, so LP plus LC is 1 here. If you're trying to follow a step, this is not going to be a problem because LP plus LC minus MR is going to be 1, and this is going to tend to 0. So with one integrator in the loop, you can follow perfectly with 0 steady state error a step signal. If you try to follow a ramp signal with one integrator in the loop, from here you can see now that in this case here LP plus LC minus R will be 0, so you'll have here a non-zero steady state error. In the case of a ramp here, this one will be equal to TS. Okay, so this is why you have TS over gamma over here. So with one integrator in the loop, you cannot follow a ramp set point with a 0 steady state error. If you want to be able to follow a ramp signal, then you have to take, well, you have to have at least 2 integrators in the loop. So in summary, if you want to, and we're now looking at the first column, you want to follow a step signal, then you need at least one integrator in the loop. If you have more than one, then you'll be able to follow the step. If you do not have any integrator in the loop, there will be a position error, in French, erreur de position ou statisme. And this position error is linked to gamma that we have introduced before, and in this case gamma is called the position error constant. If we now consider the second column, the third column we will not consider because in practice, well, this does not have much use. If we now look at this second column, well, if you want to be able to track a ramp set point, and you want, of course, a 0 steady state error, then you need at least 2 integrators in the loop. If you do not have any integrator in the loop, well, then the steady state error will be infinite. If you have one integrator in the loop, well, then you'll have a steady state error, and this steady state error will be called the velocity error. In French, erreur de vitesse ou traînée. In this case, the velocity error is again linked to this gamma introduced previously, and in this case gamma is called the velocity error constant. I consider this to be a very important table. This table is valid for set point tracking. There will be another table valid for disturbance rejection, but given a process, so given an LP, you have to be able to determine the LC that you need to choose in order to be able to track a given reference signal, either a step, this is MR is equal to 0, or a ramp, this is MR is equal to 1. We will now consider load disturbance rejection. Okay, and remember that a load disturbance is one acting on the input. And remember that we have to consider a different case here, because the transfer function that links, well, wz to epsilon z is minus pz over 1 plus pz c over z. Okay, so this is a different transfer function than the one that links, for instance, the reference signal to epsilon z. And the idea is really similar. We want to reject a load disturbance wk that is polynomial in t again, okay, with degree ml, and we want to do this with a 0 steady state error. Okay, so this means that in practice what we'll consider is either for this signal here a step or a ramp. So if you take the z transform of this one, you'll obtain a wz that takes this form, and this is exactly the same form that we had for r of z, right? And in practice ml will either be 0 or 1, and as we had also for rz, the degree of this polynomial here is smaller or equal to ml plus 1. ml here is this power. Remember, ml is equal to 0 a step, ml is equal to 1 a ramp. Well, the procedure is exactly the same as what we have done for set point tracking. This is the relation between the load disturbance and the control error, right? This is P of Z. Here we have it again. You have C of Z, so the controller. Remember that LP is something that you have to live with. It's the number of integrators in the process, but LC you can choose. You can decide on how many integrators you put in your controller. And this is, well, the type of load disturbance that you consider, and in practice you'll consider step signals and ramp signals. If you compute this, this is what you will end up with. Okay, so the idea is that again you want a 0 steady state error, right? You want this quantity here, this limit to be 0. This is the steady state error, and by the final value theorem, well, this is equal to this quantity here, and I hope it does not come as a surprise, otherwise you have to go back in the course. So to compute this limit, we take this one, we multiply by z minus 1, right? And then we take the limit when z tends to 1. This one will simplify with this one over here, and you can kind of see that if LC is larger or equal to ml plus 1, then you'll have in this limit a factor that will be a function of z minus 1. So if you take the limit, it will tend to 0. Okay, so of course again you will not take more integrators than necessary. So if you take LC is equal to ML plus 1, well, then you'll have a zero steady state error. Remember that ML, well, is really the type of load disturbance that you want to be able to reject. Notice that this condition does not involve LP. Well, this is what you have seen in the previous slide, right? We want a zero steady state error, so we want this limit to be 0, and this is equivalent to this limit over here by the final value theorem. So in here we'll consider two cases. The first one is LP plus LC is equal to 0. Well, you have z minus 1 to the power 0, so this amounts at crossing this one out, right? Now you take the limit when z tends to 1 of this one here times z minus 1. Okay, this one will cancel out with this one, right? And what you will have is, if you let z go to 1 in these polynomials, well, you replace z by 1, and this is what you've got over here, and then you'll end up with a limit which is the limit of z minus 1 to the power LC minus ML when z tends to 1. Well, if LP plus LC is larger than 0, you still have to take this limit when z tends to 1, so we have to put a z minus 1 over here. This one will cancel out with this one. The only difference is this is now something that is positive, so when z will tend to 1, this means that this one here will disappear, right? So when we take the limit, okay, what we'll see also is that this one here will disappear, and then we simply have to replace all the rest by z is equal to 1, and for z minus 1 here, well, we have to take this limit and we'll have again LC minus ML. You can draw the conclusion that if you choose LC is equal to ML plus 1, then the zero steady state error will be imposed. Okay, so again, the number of integrators in the case of a load disturbance does not depend on the process. It only depends on the type of load disturbance that you want to reject. ML is equal to 1, so a ramp, then you need 2 integrators. ML is equal to 0, a step signal, then it's sufficient to take only 1 integrator in the controller. So these are the two expressions that we had found in the previous slide. Remember that we are considering load disturbance rejection, and what you can now do is construct a table. Okay, so if LC is equal to 0, well, then we can kind of see if you want to reject a step-like load disturbance signal, well, you will have problems, okay, and there will be a steady state error. If LP is equal to 0, well, then you fall under this condition over here, and this will be the steady state error, right? Remember that in this case here RW1 is 1, and in this case RW1 is simply TS. If you're in the case that LC is equal to 0 and LP, and the number of integrators in the system, is higher than 0, then you fall under this condition over here, but the conclusion is just the same. You will have a static error. The only thing is that the expression will be different. So for a step-like load disturbance, if you want to reject it, you have to put at least 1 integrator in the system. If you want to reject a ramp like load disturbance, well, then you will have to put at least 2 integrators in the controller. If you put 0, well, then you'll have an infinite steady state error. And if you put only 1, but then you will have a steady state error that is given by this expression. This can be obtained by considering here the second case with RW1 is equal to TS. So here's the conclusion, and here we consider both set point tracking and load disturbance rejection. We are given a process that is described as follows, and what is important is that this process has LP integrators, right? And then we want to see what happens as far as steady state accuracy is concerned. Does the control error go to 0? Okay, and we want to achieve set point tracking, and the reference signal or set point signal that is considered is a polynomial of degree MR. Okay, so in practice MR will either be 0, we want to follow a step, or it will be 1, we want to follow a ramp signal, right? We want to reject a load disturbance, and this disturbance is a polynomial of degree ML. In practice, again, ML will be 0. Okay, we want to reject a step signal, or ML will be equal to 1. We want to reject a ramp signal, a ramp load disturbance. We will use a controller of this type, and the question is, what LC do we have to choose? How many integrators do we have to put in the controller in order to achieve a 0 steady state error? Okay, and the formula is given over here. It's simply, well, taking the 2 formulas that we had previously and putting them together. So this is what we had seen for set point tracking. Okay, we see that the number of integrators depends on the process there, right? And for load disturbance, well, it only depends on the type of load disturbance that you want to reject, and of course you have to take the maximum, right? So this is the conclusion, and well, you have to be able to use this formula and determine how many integrators you need to put in your controller depending on the process and the type of set point tracking problem and load rejection problem. Let us take a very simple example. We assume here that the process has 1 integrator. We want to track a step-like signal, so MR is equal to 0. We do not want to track a ramp signal. ML is equal to 0, so we want to be able to reject a step-like load signal. We do not want to be able to reject a ramp type load signal. According to this formula, well, you have MR plus 1 minus LP is equal to 0. You do not need an integrator in the controller for the tracking part. That's normal because there is already an integrator in the process. But the second part of the formula tells you that you want to be able to reject a step-like load disturbance. So you need an integrator in the loop, despite the fact that you have already one in the controller. You remember that for load disturbance rejection, well, the amount of integrators in the process does not matter. It's only influenced by the type of load disturbance that you want to reject.